Welcome to another module in this massive open online course on estimation for wireless communications. So, in the previous module we have looked at MIMO channel estimation, that is estimation of the channel matrix of a MIMO system or a multiple input multiple output wireless communication system. So, today to understand it better, let us look at an example for MIMO channel estimation. So, in today's module let us look at an example for our MIMO channel estimation, and as we have already said, MIMO stands for, just to recap a little bit, MIMO stands for multiple input multiple output, that is your MIMO, that is your multiple input multiple output wireless communication system, where the multiple inputs mean that your multiple transmit antennas to input multiple systems, multiple symbols into the wireless channel, and the multiple outputs refer to the multiple receive antennas, which basically receives multiple output symbols from the wireless channel, alright. And specifically we said, so we said that multiple inputs, basically these refer to your the multiple inputs basically are your multiple transmit antennas, and your multiple outputs are the multiple RX or the multiple receive antennas. And in this example we are going to consider a 2 cross 2. So, in this specific example we are going to consider a 2 cross 2 MIMO channel or a 2 cross 2 MIMO system. Remember, this is basically 2 cross 2, this is basically the size of the MIMO channel matrix. So, if you remember, what is the R cross T? This is the size of MIMO this is the size of the MIMO channel matrix, which is basically R cross T. So, 2 cross 2 system means basically we have a MIMO system with R equal to 2 receive antennas and T equal to 2 transmit or TX antennas, and therefore, right. So, basically I am considering a 2 cross 2 MIMO system, which is R cross T, the notation is R cross T, where R is equal to the number of receive antennas, T is equal to the number of transmit antennas. So, 2 cross 2 means you have 2 receive antennas and 2 transmit antennas. So, let me schematically represent this, just draw, although we have done it yesterday, just to refresh your memory a little bit, let me redraw it, so that you are reminded of the exact system model. So, I have a transmitter with 2 antennas called denoted by T1, T2, and on the other side I have a receiver, your receiver. So, this is your transmitter and this basically is your receiver with 2 receive antennas, let us call them R1, R2, and the channel coefficients between transmit antenna 1 receive antenna 1 is H11, between transmit antenna 1 receive antenna 2 is H21, between transmit antenna 2 receive antenna 1 is H12, and between transmit antenna 2 receive antenna 2 is H22. This is something that we have already seen. Symbol transmitted from transmit antenna 1 at time instant k is x1k, symbol transmitted from transmit antenna 2 at time instant k is x2k, symbol received on receive antenna 1 at time instant k is y1k, and symbol received on receive antenna 2 at time instant k is y2k. Therefore, I can represent this system model. This system model can be represented using vector notation as, let me just write it clearly, using your vector notation as y1k, your y1 of k, y2 of k equals your channel matrix, that is the 2 cross 2 MIMO channel matrix H11, H12, H21, H22 times x1k, x2k plus your channel noise vector V1k, V2k. So, this is your output vector y bar k, this is your channel matrix H, this is your transmitted vector x bar k, and this is the noise vector v bar k, right. So, you have the output vector, received vector y bar k, which is r dimensional, equals h times x bar, which h is the channel matrix, which is r cross t dimensional, and x bar is the transmit vector, which is t cross 1 dimensional, that is a t dimensional vector, plus v bar k, which is the noise vector, which is r dimensional, all right. So, I can comprehensively represent this using matrix notation as y bar of k equals h times x bar of k plus v bar of k. This is your r cross 1, and in this case 2 cross 1 receive vector. This is your r cross t MIMO channel matrix. This is your x bar k, which is basically t cross 1 symbol vector or transmit vector, and this is v bar k, which is basically your r cross 1, in this case r equal to 2. So, 2 cross 1 noise vector, and remember, let me remind you once again that k denotes the kth time instant, that is this denotes k denotes the kth time instant. So, we have y bar k equals h x bar k plus v bar k, that is the input output model of the multiple input multiple output wireless communication system at time instant k. Let us now consider the transmission of n pilot symbols. In this example, let us set n is equal to 3. So, let us consider. So, consider the transmission of of n equal to 3 pilot symbols, or in this case in fact they are pilot vectors, correct, because each transmitted symbol is a symbol vector, right. So, I have x bar of 1 transmitted at time that is pilot vector at time instant 1 equals 10 8. Remember, each vector is 2 dimensional because there are 2 transmit antennas. X bar of 2 equals 8 comma 10, and x bar of 3 equals your 6 comma 6. So, these are your basically these are your n equal to 3 . So, we are considering the transmission of capital N equal to 3 pilot vectors, that is x bar 1 at time instant 1, x bar 2 at time instant 2, x bar 3 at time instant 3. So, these are the 3 pilot vectors. So, corresponding to these 3 transmitted pilot vectors, we will have the 3 observed vectors y bar 1, y bar 2 and y bar 3, right. And these, let us say, are given as your y bar 1 equals let us say this is 2 1, y bar 2 equals 1 2, y bar 3 equals 1 1. Okay. And now therefore, remember we had seen that I can write the resulting equations as y bar 1 equals h x bar 1 plus v bar 1, y bar 2 equals h x bar 2 plus v bar 2, and y bar 3 equals h x bar 3 plus v bar 3. And let me remind you, this y bar 1, y bar 2, y bar 3, these are the n equal to 3 output vectors corresponding to the input pilot vectors, that is the observed vectors. So, the output pilot vectors y bar 1, y bar 2, y bar 3 corresponding respectively to the transmitted pilot vectors x bar 1, x bar 2, x bar 3. Okay. And now what we did yesterday was we concatenated these received vectors, that is y bar 1, y bar 2, y bar 3. Naturally, once you concatenate the outputs, the inputs are also concatenated. So, this is y bar 1, y bar 2, y bar 3. Each vector is r dimensional and you are putting n vectors to the side. This is r cross n, basically 2 cross 3 matrix equals H, which is as usual your 2 cross 2 channel matrix times x bar 1, x bar 2, x bar 3. This is your T cross n, basically your 2 cross 3 pilot matrix. We denoted this by x. This received concatenated output matrix, we denoted this by y, and this of course plus there is going to be your noise vector v bar 1, v bar 2, v bar 3. This is basically your noise matrix. This is your noise matrix, which is r cross, which is basically r cross n. In this example, it is therefore 2 cross 3, and this we will denote by capital V. So, I have the net system model equals, that is y equals h x plus v. This is after concatenation. This model that we have written over here is basically after the concatenation of the received output vectors and concatenation of the transmitted pilot vectors and the noise vectors. Okay. So, this is basically model after concatenation. This is basically after your concatenation. Now, therefore, let us form these matrices capital Y. Capital Y is y bar 1, y bar 2, y bar 3. So, this is basically the matrix 2 1, 1 2, 1 1. Remember, this is y bar 1, y bar 2, y bar 3, and put together this matrix is y, that is equal to your H, which is the channel matrix, times the pilot vectors x bar 1, x bar 2, x bar 3. Remember, this is your x bar 1, this is your x bar 2, this is your x bar 3, this is your pilot matrix x, plus of course, the noise matrix. The noise matrix is unknown, right. So, the noise matrix is not known to the receiver, we do not know what the noise samples are, correct. So, the noise matrix is unknown. Now, we have the observed pilot outputs, that is observed pilot vectors, that is a matrix y corresponding to a concatenation of the observed pilot vectors, the matrix capital X, which is the pilot matrix, which is basically nothing but the concatenated transmitted pilot vectors. From these two, we estimate the MIMO channel matrix H, right. So, this is your this is your observed output matrix, this is your pilot matrix, and the least squares estimate of H we had seen yesterday, your least squares estimate of the matrix of channel matrix of your MIMO channel matrix H is H hat equals, remember we derived the expression for this yesterday, y x transpose times x x transpose inverse. This is the least squares estimate of your x x transpose inverse. This is the least squares estimate of the MIMO channel matrix. So, now I will evaluate the various quantities in this estimate. First, let us start by evaluating x x transpose, and x x transpose is basically the matrix X, the pilot matrix X, which is 10 8, 8 10, 6 6 times its own transpose, that is 10 8 6 8 10 6. Okay. And this, therefore, now we can simplify this. I am going to write the answer over here. This is equal to 200, 196. So, this is of course going to be a 2 cross 2 matrix, 196, 200, and this is basically your x x transpose, where x is the pilot matrix. So, first we are computing the matrix x x transpose. Now, next of course, we have to compute x x transpose inverse. Okay. So, x x transpose inverse is the inverse of this two cross 2 matrix x x transpose. The inverse of this is a 2 cross 2 matrix. So, the inverse can be computed rather easily, that is 1 over the determinant 200 square minus 196 square times you interchange the diagonal elements and negative of the off diagonal elements, that is minus 196 minus 196, and now this can be simplified as you can see 1 over 200 square minus 196 square, that is 1 over 4 into 396 times 200 minus 196 minus 196 200, yeah, and this cancelling the factor of 4, this is basically equal to, what you get is this is basically equal to 1 over 396 times 50 minus 49 minus 49 and 50. Okay. So, this is basically what you get. And now, if you look at y x transpose, so we have computed x x transpose inverse, y x transpose, where y is the observed output pilot matrix 2 1 1 2 times 10 8 6 8 10 6, which is equal to this matrix 34 32 32 34, and therefore, we have computed both these components. We have computed y x transpose, x x transpose inverse. Now, the channel estimate H hat, the ML estimate, in fact, the least squares estimate of the channel matrix H is given as H hat equals y x transpose times x x transpose inverse, correct. So, now I can compute h hat as basically something that we already written, y x transpose times x x transpose inverse. Now, y x transpose is something that we have just computed. Let me just write it down over here, 34, 32, 32, 34 times x x transpose inverse, that is something that we computed before, 1 over 396, 50 minus 49 minus 49, 50. Let me just bring out this constant factor of 1 over 396. So, 1 over 396 times 34, 32, 32, 34 times this matrix 2 cross 2, which is 50 minus 49 minus 49, 50, which is equal to 1 over 396 times 132, and you can check this 132 minus 66, 132 minus 66 minus 132 minus 66 minus 66 132, and if I simplify this, basically my h hat equals, on simplification you can check that h hat is 1 over 3, 1 over 6 or minus 1 over 6 rather, minus 1 over 6, 1 over 3, and this is basically your 2 cross 2 MIMO channel. This is the estimate of your 2 cross 2 MIMO channel. So, what we have derived here, we computed, in fact this is a estimate or basically the least squares and also the maximum likelihood estimate. So, you can term this either as the least squares estimate, or in fact the least squares itself is derived from the maximum likelihood principle. So, you can also term this as the maximum likelihood estimate. Basically your ML estimate. Maximum likelihood or ML estimate of the channel matrix H. Okay. All right. So, basically what we, so this is 1 over 3 minus 1 over 6 minus 1 over 6 1 over 3, that is the estimate of the 2 cross 2 MIMO channel matrix. Okay. So, this simple example basically illustrates how we compute using the least squares principle or the maximum likelihood, which is in fact derived from the maximum likelihood principle, how we compute basically the estimate of the 2 cross 2 MIMO channel matrix. In fact, the derived expression is general that can be used to compute the estimate of any R cross T MIMO channel matrix. This example illustrates its application for the estimation of a simple 2 cross 2 MIMO system for n equal to 3 transmitted pilot vectors. So, what we have done in this module is basically illustrated this principle of least squares based estimation of the MIMO channel matrix. First, we have formulated the system model for this MIMO transmission and reception, that is transmission of the symbol x bar k, reception of the symbol y bar k. We have demonstrated that that is y bar k equals h times x bar plus k plus v bar k. Considered the transmission of 3 pilot vectors x bar 1, x bar 2, x bar 3. The reception of 3 output vectors y bar 1, y bar 2, y bar 3, concatenating the transmitted pilot vectors as the matrix x, the received output, the observed vectors as the matrix y. We had earlier derived that the least squares estimate of the channel matrix is given as by y x transpose times x x transpose inverse. We have substituted basically the transmitted pilot vectors and the received or the observed output vectors to basically compute the least squares estimate of the MIMO channel matrix H hat. Alright. So, this example comprehensively illustrates the application of the least squares principles and the maximum likelihood paradigm for MIMO channel estimation, that is multiple input, multiple output wireless channel estimation. So, we will stop this module here and explore other aspects in subsequent modules. Thank you very much.